The renin angiotensin aldosterone system is one of a very important system in the body that is responsible for regulating blood pressure and fluid balance. Today, we are going to have a physiological review of the RAS system ahead of our discussion about the drugs that influence it. As we know, when we talk about drugs are chemical substances that are going to influence body function. So that means you really first need to understand physiology, and then you'll see how drugs come to fit within a physiology gone wrong. Hello, my name is Judith All Saints Appeal, and welcome to my channel Pharmacology and Packs for Nurses. Have you tried to read through the physiology of the renin angiotensin aldosterone system and you thought that things were not making sense? Or have you tried to read about the ACE inhibitors, the angiotensin receptor blockers, and try to understand them and you found you are getting stuck somewhere? So what we are going to do at this time is going to be a review of this system such that once you've understood it, you're going to see how the drugs just fit in really nicely. So let's pick whatever it is we have, that notebook, and get ready for our review of the RAS system. So in terms of outline, we are going to look at the function of the renin angiotensin aldosterone system, the key players, the triggers, the mechanism, and then finally we will discuss the implication of this system for nursing practice. Because while we need to know how the body functions, all right, we also need to understand when things go wrong and how things can go wrong. In that way, we will be able to understand how our interventions can come in to help. And of course, one part of that intervention is the use of medications and how medications can reverse a pathophysiology back to a physiology. So we are going to start off with the function. First is going to be regulating vascular tone, okay? The RAS regulates vascular tone. Tone is the state of contraction or relaxation within muscles. So vessels contain smooth muscles. How relaxed or how constricted are those vessels? Okay, we are going to regulate sodium and water homeostasis, and both of these are eventually going to contribute to a regulation of blood pressure. Okay, think about it this way. Pressure is a product of cardiac output times total peripheral resistance. Can these two factors lead to fluctuations in pressure? If we have an increased tone within the vessels, it means that resistance within the vessel is also going to increase, and blood then will flow with increased pressure. And then if, for example, we have an elevation in blood volume, then pressure will also be increased because of the increase in fluid volume, and vice versa. So that's how the RAS system regulates eventually blood pressure. So who are they that are responsible and involved in this beautiful system in the body? So when we talk about the players, we're going to look at three categories of things. The first player, I'm going to call them the organ systems. Okay, so the organ systems include the liver, the kidneys, the lungs, the vessels, the brain, and the adrenal gland. And each of these has a specific role that it plays in the renin angiotensin aldosterone system. The second thing that we are going to talk about are the hormones. The hormones that are involved in the renin angiotensin aldosterone system include these three: angiotensin 2, aldosterone, and then ADH, or antidiuretic hormone. The third player are enzymes. We have two. The first one is renin. The second enzyme is the angiotensin converting enzyme, also usually called the ACE. In summary, the players in the RAS system include organ systems that include the liver, the kidney, lungs, the vessels, the pituitary gland, and the adrenal gland. And then we do have hormones, and those hormones include angiotensin 2, and then we will have aldosterone, and then we will have antidiuretic hormone. The enzymes will include renin and ACE, or angiotensin converting enzyme. Let's look at the third part, which are the triggers of the renin angiotensin aldosterone system. Three things can set off the RAS system in motion, and it usually begins within the kidneys. So the first trigger would be a reduction in blood pressure if blood is flowing with less pressure to the kidneys. So reduced renal perfusion pressure. And then the next one is going to be when we have a reduced delivery of sodium to the distal convoluted tubule. That's the second trigger for renin to be released by the kidney and to set this entire thing into motion. And then finally, we are going to have stimulation of the sympathetic nervous system via the stimulation of the sympathetic nervous system via the beta-1 receptors that are located in the juxtaglomerular apparatus of the kidney. So we are going to look at how these play out, and then we will finally talk about the mechanism. The first trigger is when we have blood that is flowing through the afferent arterioles with low pressure. So in other words, reduced renal perfusion pressure. So let's say we have blood that is flowing into the glomerulus through the afferent arterioles. A memory aid that you can use to remember the afferent arteriole and also to know what its function is looking at this first letter of afferent and just say A is equal to access. So the afferent arteriole is an access route for blood into the glomerulus, while the efferent arteriole is where blood exits. So this E would be to exit the glomerulus. The first trigger is a reduction in the pressure with which blood is flowing through the afferent arterioles. So we are going to have reduced blood pressure, and this can happen in many situations. Maybe your patient has had massive hemorrhage, then the blood volume is low. Of course, if the blood volume is low, it's also going to flow with less pressure. And because we're having a low cardiac output, the kidney receives little. So little blood is flowing to the kidneys with little pressure. So when that blood flows through the afferent arterioles, we have specialized cells that line the afferent arterioles. These cells are called the juxtaglomerular cells. These cells are baroreceptors that sense sensations of pressure, fluctuations in pressure. So the juxtaglomerular cells are going to sense that blood is flowing through the afferent arteriole with less pressure. And if that happens, these cells will release renin. And you see that we would have set our RAS system into motion. Blood flowing through the afferent arterioles with less pressure is going to trigger the juxtaglomerular cells to release renin in response to the reduction in blood pressure. Okay? Then the second thing is when we have little delivery of sodium to the distal convoluted tubule. You know that blood is coming through the afferent arteriole and then it's going to be filtered in here. And whatever is filtered gains or enters the Bowman's capsule and then into the proximal convoluted tubule. Okay? And usually the kidney is going to filter everything. Then whatever is required by the body is going to be taken back into the body or is going to be brought back into blood. So as the filtrate is moving through the length of the nephron. We are going to have sodium being reabsorbed. By reabsorption, we mean sodium is leaving the nephron and going back into blood. At the proximal tubule, you have almost about 65% of sodium being reabsorbed. Okay, so this is sodium that is leaving here and coming into the blood. Then the remainder of the filtrate continues its journey, and once it reaches the loop of Henle, about 35% of sodium being reabsorbed yet again back into the blood. Then the remainder that is there continues its journey to the distal convoluted tubule. And at the distal convoluted tubule, you will find about 5 to 10% of the remaining sodium being reabsorbed back into blood. Now, if the amount of sodium that is reaching here is low, it is also going to trigger the release of renin. How does it happen? So imagine that blood was flowing with less pressure, then it was filtered, so the filtrate is here. Because the filtrate is also flowing slowly, there is increased contact time in these earlier segments of the nephron. So that gives much time for sodium to be absorbed much early before it reaches the DCT, such that by the time it reaches the DCT, we are having less than this percentage. And the junction of the loop of Henle, the end of the loop of Henle and the beginning of the distal convoluted tubule, we have very special cells here. These cells are known as the macula densa cells. These cells are chemoreceptors. They are going to sense the concentration of chemicals in blood, and specifically here, they are going to sense the concentration of sodium that is flowing in the filtrate and reaching the DCT. And once it picks that it is low, it is also going to trigger the juxtaglomerular cells to release renin. In fact, we can say that the juxtaglomerular cells and the macula densa cells form what we would call the juxtaglomerular system, because stimulation of both is going to lead to a release of renin. The third trigger is going to be stimulation of the sympathetic nervous system. So, in the juxtaglomerular apparatus here, we have receptors of the sympathetic nervous system, specifically beta 1. Again, when blood is flowing with less pressure, the sympathetic system is stimulated to release catecholamines, norepinephrine. That is going to bind the B1 receptors that are located here. And then that binding is also going to cause a release of renin. So those are the three triggers for renin release. Now let's look at the actual mechanism of the renin angiotensin aldosterone system. Renin has been produced by the juxtaglomerular cells that are lining the afferent arterioles that are taking blood into the glomerulus. In fact, they're called juxtaglomerular cells because anatomically they are juxtaposed. They are just close to the glomerulus. So renin is released, of course, into blood, and the liver produces certain substances, certain inactive proteins, and one of those is angiotensinogen. When you see something ending in ogen, when you see this, just know that that is inactive. For it to be able to work, it has to be activated. So the liver produces a number of those. And another example apart from angiotensinogen would be fibrinogen, plasminogen, those that we see especially in the coagulation cascade. When the liver produces angiotensinogen and it is also there in blood and the kidney has released renin. So all this is circulating in blood. So the renin circulating in blood is going to meet angiotensinogen. And what does renin do? Renin is going to activate angiotensinogen by cleaving off a part of it that makes it inactive. So renin will cleave this part. Renin is going to cleave this so that you end up with angiotensin 1. So we'll call that angiotensin 1. So renin catalyzes the cleavage or the activation of angiotensinogen to angiotensin 1. This is happening within the circulation. So angiotensin 1 also continues with its journey. Incidentally, angiotensin 1 is quite unstable. It also does not really have a specific function that it plays in the body, and it is readily converted to angiotensin 2. So as it is flowing, blood is going to flow and then gets into the lungs. The lungs produce these special enzymes called the angiotensin converting enzyme, which is going to convert angiotensin 1 to angiotensin 2. All right? Yeah. Now, once we form angiotensin 2 is really our product of interest. Angiotensin 2 plays a number of functions in the body that are very important in regulating vascular tone and then sodium and water balance. Now, angiotensin 2 is going to have effects on different areas. And these effects, of course, are going to be mediated through receptors. And the specific receptor that mediates this effect will be angiotensin receptor subtype 1. So angiotensin 2 is going to bind to its receptor and then bring about effects in these different areas. So let's start by looking at the effect of angiotensin 2 on the vessels. Now, angiotensin 2 is one of the body's most potent vasoconstrictors. Potency is the amount of something that causes an effect. So when we say something is potent, we really do mean that in very small amounts, that thing is able to produce a massive effect. So angiotensin being a potent vasoconstrictor means that small amounts of angiotensin causes high levels of vasoconstriction. So the effects of angiotensin 2 are seen in vessels almost all over the body, okay? So you have vessels all over the body. You have vessels that are leading to the kidneys as well. So what happens? Angiotensin 2, so if this was our vessel, okay? So let's assume that was our vessel. Now, when angiotensin 2 through its receptor acts on this vessel, it is going to constrict the vessel. So the vessel lumen here is going to be reduced. Okay? The vessel lumen here will be reduced. So you find that these are areas of contraction, and then this is now the lumen that we will have. Okay? You see how constricted it is? Now, because of that constriction, when blood tries to flow through it, blood meets an area of resistance, and to offset that resistance, it flows with increased pressure. So in other words, then we say the effects of angiotensin 2 on vessels is to cause vasoconstriction. And then if we cause vasoconstriction, we are going to end up with an increased systemic vascular resistance, which eventually will increase the pressure with which blood is flowing. This is happening in other vessels. This is also happening in the kidneys. Angiotensin has effects really on both the afferent and efferent arterioles. However, it affects the efferent arterioles most. What does it do? It's also going to constrict this vessel. And when it constricts this vessel, imagine you're going to have an area here where the lumen is reduced. Remember, blood is supposed to be flowing in this direction and moving there, but because you have this constricted area, you really don't have so much blood moving to that area. So what happens? That blood is held or backs up within the glomerular system, and that is going to increase the glomerular filtration pressure. The second effect of angiotensin 2 is going to be in the brain and particularly in the pituitary gland. What does angiotensin 2 do? Angiotensin 2 is going to trigger the pituitary gland to release antidiuretic hormone, ADH. Antidiuretic, something against diuresis, against water loss. ADH also has its effects, okay? In fact, you should interest yourself in knowing that ADH is also a vasoconstrictor. So ADH will also cause vasoconstriction. And the second thing ADH is going to do, reabsorb water from the collecting ducts. That area is impermeable to water as long as ADH is not there. But once ADH is released, the collecting duct is going to be permeable to water, and then water will be able to move back into the bloodstream. Now, again, we're having vasoconstriction, we're having water, so we are increasing resistance within the vessels, we are increasing volume. End of the day, you have an increased BP. Third effect of angiotensin 2 is on the adrenal gland. All right, so especially angiotensin 2 is going to stimulate the adrenal cortex to release the hormone aldosterone. Okay, remember the renin angiotensin aldosterone system. Aldosterone is a mineralocorticoid, minerals. Aldosterone regulates the concentration of sodium and potassium. Aldosterone exchanges sodium for potassium within the late part of the distal convoluted tubule of the kidney and the collecting duct. So what is going to happen? Aldosterone is going to cause reabsorption of sodium plus water. However, in so doing, aldosterone is going to cause potassium excretion. So we lose potassium, we gain sodium. Look at it. We've also increased blood volume here. So we have increased blood pressure. So after understanding the mechanism of the renin angiotensin aldosterone system, you see that we started with a trigger of a reduced blood pressure, and now we are ending up with a correction of the blood pressure by the different players performing their respective roles to ensure that blood is flowing with adequate pressure through two mechanisms, through increasing resistance within the vessels and increasing the blood volume. The fifth part, which is the implications of the RAS system to we as nurses. What does it exactly mean? All right. Now, after looking at what the RAS system does, or what angiotensin 2 does to the body, increasing vasoconstriction, increasing the volume of blood, what is it going to do? Now, the RAS system has implications in either fueling certain diseases or actually causing them. And we have three main conditions. So angiotensin 2 can actually play a role in the pathophysiology of hypertension, as well as the pathophysiology of heart failure, and even in renal disease. So think about it this way. You have blood that is flowing with a lot of pressure. Vessels are constricted. The effect of angiotensin 2 through its receptor subtype 1 causes a number of effects. One, it is going to increase cellular proliferation. Okay, it's going to increase proliferation of cells. Angiotensin 2 is also going to cause hypertrophy. So this can be a hypertrophy of both vessels and the heart itself, because demand is being increased in all those systems. Angiotensin 2 can even cause cellular apoptosis, okay, programmed cell death. Now, because of the sustained increase in resistance within the cells, those and within the vessels, those vessels are going to hypertrophy. And when they hypertrophy, we say a remodeling is happening. There are structural changes that are taking place in the vessel. Those structural changes make the vessels more fibrotic and more tough, so they don't really stretch or expand or relax like we would want it to allow blood to flow through. So that has implication in causation of hypertension, right? Yeah. If we have sustained or exaggerated angiotensin 2 effect on the blood vessels, we are going to have a sustained elevation in blood pressure, which can damage those blood vessels and damage the organs that are supplied by those blood vessels. One of the organs will be the heart and then the kidneys. I mean, if there is constriction of the efferent arterioles and we are having an increased glomerular filtration pressure, if that pressure continues to be sustained, it is detrimental to the kidneys, okay? So in other words, we've seen that angiotensin 2 can fuel hypertensive disease. It can also fuel renal disease. Then, because we've increased the volume that the heart needs to handle, the heart is going to pump harder, the heart is going to pump faster. In other words, the heart is put under a lot of demand. Because of that, the heart muscle, the left ventricle, first of all, is going to start by dilating. So we are going to get a dilation. After that dilation, we have a hypertrophy. Now, when that happens, this is what you would expect to see. Let's have this to represent our left ventricle, okay? And this is the wall of the left ventricle. Now, this is the wall of the left ventricle. The wall of the left ventricle and the lumen of the left ventricle should allow it to perform its function effectively. There are two things that the left ventricle is going to do. First of all, it's going to receive blood from the left atrium, okay? And then, after receiving that blood from the left atrium, it is going to pump a fraction of that blood to the rest of the body through the aorta. And you know that the aorta is a large artery and blood flows through it with a lot of pressure. So the left ventricle has to really offset that pressure. Now, if we are having dilation and eventually hypertrophy, this wall is going to be thickened further. Okay? It's going to be thickened further. Now, what do you notice is happening? The lumen is reducing. Now, because the lumen is reducing, it's going to fill up with less blood than it usually would do. Okay? That means that if it's less blood, it's also going to pump less blood as our cardiac output. Then, because the wall has also now become really thick, it does not pump effectively. So you find that its two main functions have become compromised. Its contractile force to eject that blood out into the aorta, and then also its filling, because the space will be reduced. So when that happens to the vessels, when this happens to the vessels and to the heart, so we say the cardiovascular system is undergoing a remodeling. Okay? CVS remodeling are structural changes that occur in the heart in response to an increased demand in trying to keep up with the demand. So it's more like a compensatory mechanism. The RAS system does that. I usually want to say, and I usually explain it to students as the RAS system coming in with a very good intention to improve the pressure with which blood is flowing, but at the end of the day, in doing so, it is also creating some problems in the body. So in fact, hypertension, heart failure, and renal disease are fueled by the RAS system. That is why, as another part of our implication, we have drugs that can block the RAS system so that we may prevent these conditions from happening, or we can slow down the progression of disease. We can use drugs to block production of renin. We can also use drugs to inhibit the ACE, and we can use drugs to block this receptor. So here we would use the angiotensin receptor blockers, or the ARBs, that are going to bind the angiotensin 2 receptor subtype 1 and prevent angiotensin 2 from binding. Then we will have a reversal of these effects. Or we may block ACE so that angiotensin 1 is not converted to angiotensin 2. In other words, we are not producing angiotensin 2. Or we can block it from the source. Can we block renin with a renin inhibitor? So here we would use the ACE inhibitors, and then here we would use the renin inhibitors. I am sure we are very conversant with the ACE inhibitors and the angiotensin receptor blockers. But in our next review, I'm also going to introduce to you the renin inhibitors, which are kind of like a new advance in trying to utilize our understanding of the RAS system in blocking renin to see if we can also help in managing these conditions. That is the review of the renin angiotensin aldosterone system. I hope that it has made your life a little bit comfortable and made your work easy. Watch out for our next recording, where we will talk about these drugs. For nurses who are taking the NCLEX, you know that drugs that influence the RAS system is one of those very important drugs that you need to know under your cardiovascular system pharmacology. And we do not exclude the students at school. You do need to know about them. So watch out for that recording, where we will break it down for you. Also, if you have any suggestions of any topics that you'd like me to record for you, please suggest it in the comment section and I will be able to consider it. If you have benefited from this and you hope that even in future you're going to still meet a lot of such discussions, please subscribe to my channel and then like this video and share with your colleagues, share with your friends, share with your fellow nurses and the fellow students, share with all the NCLEX takers, okay, such that this may reach a wide audience and we can all benefit from it. I thank you all for listening to me. Let's watch out for our next class. Thank you.